Good day to everyone. Welcome to our presentation of hydrocarbons. Today, we'll explore three of the most important classes of organic compounds: carboxylic acid, esters, and amides. These compounds play significant roles in various industries from food and pharmaceuticals to polymers and cosmetics. Our journey today will include naming conventions, properties, sources, and uses of these compounds. Let's begin with carboxylic acids. Introduction of what is carboxylic acid. A carboxylic acid is an organic compound with a carboxyl group, which includes a carbonyl group and hydroxyl group. It exhibits acidic properties and is found in many natural and synthetic substances.
First, let's take a closer look at carboxylic acids. We'll start by understanding the rules for naming them, which is fundamental in organic chemistry. Rules for naming carboxylic acids. When naming carboxylic acids, we follow a systematic approach set by IUPAC. The first step is to identify the longest carbon chain that include the carboxyl group. This is important because the carboxyl carbon is considered part of the main chain. Next, we replace the ending of the parent alkane with oic acid. For instance, if our longest chain is propane, a 3-carbon chain, it becomes propanoic acid when we add the carboxyl group. We then number the carbon chain starting from the carboxyl carbon, which is always carbon 1. This helps in accurately indicating the position of any substituent attached to the main chain. These substituents are prefixed with their position to the base name. In cases where multiple carboxyl groups are present, we use special naming convention. For example, if there are 2 carboxyl groups, we use the prefix dioxic acid. An example is ethanol dioxic acid, where di indicates 2 carboxyl group. Additionally, many carboxylic acid have common names that are widely accepted. For example, methanoic acid is commonly known as formic acid, and ethanoic acid is known as acetic acid. These common names are often used in industry and academia.
Now that we understand how to name carboxylic acids, let's explore their physical and chemical properties to see how these compounds behave. Properties of carboxylic acids. Carboxylic acids exhibit interesting physical properties. Many are colorless liquids with strong, often unpleasant odors, especially those with 5-chain carbon atoms. However, as the carbon chain length increases, these acids become wax-like solids with less pronounced odors. A remarkable characteristic of carboxylic acids is their strong hydrogen bonding between molecules. These results in higher boiling points compared to other substances of similar molar mass. Additionally, they can hydrogen bond with water molecules, making those with 1 to 4 carbon atoms completely miscible in water. However, as the carbon chain lengthens, solubility in water decreases. For instance, hexanoic acid is barely soluble, while palmitic acid is essentially insoluble. Despite these, they remain soluble in organic solvents like ethanol and diethyl ether. Chemically, carboxylic acids are weak acids that ionize slightly in water to form moderately acidic solutions. They react with bases like NaOH or sodium hydroxide to form salts and water. For example, acetic acid reacts with sodium hydroxide to form sodium acetate and water. Long-chain carboxylic acid salts, known as soaps, have practical applications in cleaning and hygiene products.
Sources of carboxylic acids. Carboxylic acids are found in various natural sources. For examples, citrus fruits like oranges, lemons, and limes are high in citric acid. Formic acid is found in insect venom, acetic acid in vinegar, and benzoic acid in plants. Chemically, they are produced by oxidizing primary alcohols and aldehydes. Acetylsalicylic acid, better known as aspirin, is a modified version of salicylic acid and is a common pain reliever, highlighting the importance of carboxylic acids in pharmaceuticals.
In the food industry, carboxylic acids like acetic acid are used as preservatives, flavoring agents, and pH regulators. They play a crucial role in maintaining food quality and safety. In pharmaceuticals, many drugs contain carboxylic acids as active ingredients. Aspirin is a widely used pain reliever and anti-inflammatory drug that contains a carboxylic acid group. In cosmetics, carboxylic acids are used in skin creams, lotions, and shampoos for their exfoliating and moisturizing properties. For example, glycolic acid and salicylic acid are popular ingredients in skincare products.
Introduction of what is ester. Esters can be used in solvents, flavorings, and fragrances. They are recognized for their fruity scents. Through hydrolysis, they might decompose into the original acid and alcohol.
Naming esters involve a few simple steps. First, we name the alkyl portion of the ester, followed by the acyl segment. The alkyl group's names correspond directly to the R group present in the ester. We modify the corresponding carboxylic acid's name by dropping the IC acid ending and adding the suffix "-ate". For example, the ester formed from methanol and acetic acid is named methyl acetate.
Now that we know how to name esters, let's explore their physical and chemical properties. Properties of esters. Esters have distinct physical properties. They are polar molecules, but unlike carboxylic acids, they cannot hydrogen bond with each other because they lack a hydrogen atom directly bonded to oxygen. These results in lower boiling points compared to the isomeric carboxylic acids. However, esters can hydrogen bond with water molecules, making low molar mass esters somewhat soluble in water. Esters with 3 to 5 carbon atoms have borderline solubility. These properties make esters useful for solvents in various applications, such as ethyl acetate, which is used for extracting organic solutes and making lacquers. Next, let's look at how esters are prepared. Preparation of esters. Esters are typically prepared by a reaction known as esterification, where a carboxylic acid reacts with an alcohol in the presence of a mineral acid catalyst, producing an ester and water. For example, acetic acid reacting with ethanol produces ethyl acetate and water. In industrial applications, condensation polymerization involving dicarboxylic acids and dihydric alcohols yields polyesters like polyethylene terephthalate or PET, which are used in fabrics and bottles. Let's now discuss the hydrolysis of esters. Hydrolysis of esters. Esters can be hydrolyzed in the presence of an acid or base. Acidic hydrolysis is essentially the reverse of esterification, producing a carboxylic acid and an alcohol. In basic hydrolysis, also known as saponification, an ester reacts with a base to produce a carboxylate salt and an alcohol. Unlike acidic hydrolysis, saponification goes to completion.
Sources of esters. Esters are formed by combining alcohol and carboxylic acid and are found naturally in fruits and flowers. Their pleasant flavors and fragrances make them valuable in food, cosmetics, and perfumes. In industry, esters are used as solvents and plasticizing agents.
In medicine, Ester benzocaine is widely used as a topical anesthetic to temporarily numb the skin. It's found in over-the-counter products like creams, gels, and sprays. Esters are also used in fragrances and flavors. For example, ethyl butyrate provides the characteristic scent of pineapple and is used in food flavorings and perfumes. As solvents, esters like ethyl acetate are used in nail polish removers and paints, while methyl acetate is used in adhesives and coatings.
Introduction of what is amides. Amides are organic substances that have a nitrogen atom bonded to a carbonyl group. They are frequently found in proteins and are utilized in a variety of fields, including polymers and pharmaceutical.
Roles in naming amides. Amides are formed by the reaction of carboxylic acids with amines, eliminating water molecules. When naming amides, we change the suffix of the carboxylic acid from OIC acid to amide. The substituents are numbered in the amide carbon and arranged alphabetically. Examples include propanamide and formamide.
Let's now explore the properties of amides. Properties of amides. Amides exhibit unique physical properties. Most are solid at room temperature, except for formamide, which is a liquid. They have high melting points due to strong hydrogen bonding. Low molecular weight amides are soluble in water because of their ability to hydrogen bond with water molecules. Chemically, amides are less reactive than esters and carboxylic acids. They can be hydrolyzed to carboxylic acids and ammonia or amines under acidic or basic conditions. Unlike carboxylic acids, amides do not act as acids or bases in aqueous solutions.
Sources of amides. Amides are produced from carboxylic acids, ammonia, or amides. They are present in proteins and plant alkaloids. The amide group is also found in commonly used medications like paracetamol, highlighting their importance in pharmaceuticals.
In the pharmaceutical industry, amides are frequently used in medications. Acetaminophen, a pain reliever and fever reducer, contains an amide functional group. Another example is melatonin, used to treat insomnia and jet lag. In the polymer industry, amides are used to produce synthetic polymers like nylon, which is made from hexamethylenediamine and adipic acid. Nylon is valued for its strength and durability, making it useful in clothing, carpets, and ropes.
In conclusion, carboxylic acids, esters, and amides are essential organic compounds with diverse structure, properties, and applications. Carboxylic acids are notable for their acidity and use in food and pharmaceuticals. Esters are prized for their pleasant aromas and used as solvents and plasticizers. Amides play a critical role in pharmaceuticals and the polymer industry. Understanding these compounds enhances our appreciation of their roles in everyday product and industrial processes. This concludes our presentation. Thank you again for listening.